We have a quiz this Friday, so you're all up for that. And that will happen the first thing when we get in here. So first 15 minutes will be that. It's a closed notes quiz. So any questions about it? Are we all set?
Friday.
Well, what we started discussing yesterday was looking at the kinds of behavior of systems that can actually be measured. And we focused quite a bit on phase behavior yesterday. And right at the end, we started to consider volumetric behavior. That is, the things that can be described by volumetric or PVT equations of state. So there's where I want to start today. And there are different ways of representing them. Let's see if that was my first slide, yeah. And the first of them, of course, is the ideal gas law that we all know and love and can make use of. It's important to point out that it's not just a laboratory curiosity. The ideal gas law holds over many of the situations that we actually encounter in practice. If we're willing to tolerate up to a 2% error, then we're probably good anytime the molar volume is greater than about 20 liters. And that covers a lot of cases, but not all. So there are situations, of course, when this isn't going to be good enough and we need to generalize the behavior. And that generally kicks in when the pressure starts to get higher. As the pressure is low enough, everything is an ideal gas. But as we start to move the pressure up, then the molecules are, on the average, close enough to one another, then we expect that there might be some intermolecular attractive interactions. The first really good way of describing this was proposed by Van der Waals way back in 1873, and you're all familiar, I think, with the Van der Waals equation of state, which involves two parameters here, A and B, which have physical significance. B is the so-called co-volume, or the actual volume of the molecules, meaning that the volume that is free for the molecules to move in excludes their own presence. So that occurs here. We have to subtract it off from the volume available. And then A is an account for the intermolecular attractive forces that exist, so that the pressure we would have under given conditions would be somewhat less than we would expect from the ideal gas law because of these attractive interactions. So we see a negative term here, which is as we would expect. Now, there's a fairly considerable database, particularly in the older literature, that has been built up for A and B, just empirically fitting data for various gases. But that generally isn't what is used anymore, even when we want to implement the Van der Waals equation. Instead, what we make use of is the general behavior of materials that allow us to extract values for A and B from critical point data. Now, you may recall that, let's see if I can make this without screwing it up. It's a little bit hard to write on this stuff. But remember when I had a PV phase diagram, it looked something like this. There's the two-phase envelope, and the critical point, or the critical temperature isotherm looks like this, and where it passes through the critical point, it undergoes a mathematical point of inflection, which means that both the first and second pressure derivatives with respect to volume at that point are zero. So that's two equations, so that should suffice for us to evaluate two unknowns. In this case, those unknowns are A and B. So if I do that here, I just carry out the differentiations of the Van der Waals equation as written. This is what happens. And what I can do is use the Van der Waals equation itself to eliminate the critical volume, VC, from these equations, and ultimately then get expressions for A and B in terms of the critical temperature and pressure. So this is the way we will normally get values of A and B for use in the Van der Waals equation. Everyone see that? You probably worked with this before, I'm not sure. Well, the Van der Waals equation never gives us a ridiculous result, no matter what. It'll describe not only gases, but it should, in principle, take us through and describe even liquid phase behavior for the given substance. So, at least in principle, it's fairly general. But as you would expect for an equation that only has two parameters in it, that it would probably not be able to do a good enough job to actually use it for design purposes. So quite a bit of effort was put into trying to tweak this equation a bit to make it better, but without having to introduce any additional parameters. And it's widely believed, well, I guess I'm getting a little ahead of myself. Let's look at an example with the Van der Waals equation first. So let's imagine we want to describe here the volumetric behavior of carbon dioxide, as described by the Van der Waals equation. So here's our A and B expressions in terms of the critical point properties. So here we have them, we can look them up in the table. Critical point temperature, 304.2 K. Critical point pressure, 73.76 bar. We're going to need a value of R as well, so we can put that in. That's 83.145 cubic centimeter bar per mole degree K. So we have everything we need to evaluate A and B, and here are those calculations. You can see them here. And so when I plug in the numbers for A and B, this is the equation that, see if I can get that to go back to size, this is the equation that describes carbon dioxide. So I could prepare some isotherms for that just to get an idea of what it would look like. And here are a family of them. You can see the critical point, here's a critical point here, so here's my temperature, 304.2, that's a critical point temperature. I've got one isotherm above that, and then several of them beneath that to see what they look like. And this is interesting because what it suggests is that I can describe the behavior all the way from the gaseous region, maybe I do this gaseous region over here, going smoothly without any noticeable phase change over into the liquid state that exists over here. So that's kind of interesting. And we're going to want to explore what it is that's actually going on here in between these liquid and vapor regions. Because at any one of these isotherms, it looks like we can describe it as moving continuously from one phase state to the other. So we'll explore that further when I get into it. But now I can get back to what I was saying about trying to do a bit better with just two parameters. Yeah.
I want to just confirm for me what we learned in 325. Those little dips right there at the bottom of each isotherm, those aren't real, right? Those are...
I'm going to explore that now.
Okay.
Parts of them are real and parts of them are not. So it's an interesting story. There's a lot of useful information in those curves that are underneath the two-phase dome. So it's widely believed that the best two-parameter representation we have is the so-called Redlich-Kwong equation, and it looks a lot like the Van der Waals equation, but the second term is tweaked a little bit. So it also has the parameters A and B, but we better put subscripts on them to remind ourselves that those are not the same as the Van der Waals A and B, so the Redlich-Kwong ones. But I can do the same thing I did before, that is set the first and second derivatives of p with respect to v equal to 0 and solve for the Redlich-Kwong constant. So same procedure there, and there's the result that comes out of that. Still not good enough for design purposes, though even it is a little bit better. So somehow if we're going to do better, we're going to need more parameters. In particular, let's consider the possibility of adding a third parameter, and a lot of suggestions have been made. But it's boiled down to pretty much something that is exemplified by what is called the Peng-Robinson equation. And let's take a look at that. There's a number of things I need to say about this. So the Peng-Robinson equation has an architecture that looks pretty much like the Van der Waals and Redlich-Kwong equations. Here the first term is exactly the same structure. Second term a little bit more complicated. And we can see this is the way the book lays it out. Breaks it up into these terms. So here I've got alpha as a function of temperature. Here I can use the critical point information to get A and B. But alpha here is 1 plus kappa here times 1 minus the square root of the reduced temperature. So temperature is involved here. That's T over Tc, and this quantity is squared. But what's important is what this kappa is, and it in turn is expressed in as a function of this thing called omega, which is the eccentric factor. And I want to say some things about that. So my eccentric factor, when it all boils down, is my third parameter. But the eccentric factor here has a rigorous definition that I want to look at. I think I just put a little box around it because I think this deserves some attention. This is the way it's defined. It's minus 1.000 exactly here, minus the common logarithm of the reduced vapor pressure at a reduced temperature of 0.7. So that's a bit of a mouthful, but when you look at it, what you see is that the acentric factor basically implements a data point from the vapor pressure curve. It implements what it contains here informationally is the vapor pressure at a reduced temperature of 0.7. Reduced temperature of 0.7 is roughly room temperature for many, many things. So it's a convenient one, but it requires here that we have vapor pressure information. So in a sense, this really isn't a third adjustable parameter at all. It's actually just implementing other data. It looks like a third parameter when we put it in the Peng-Robinson equation, but in fact, it requires vapor pressure data for its evaluation. Now it should be, you should look at this carefully and see how, the standard question you could be asked, well, how do I evaluate this? Well, if I have Antoine's equation for it, then I can evaluate the vapor pressure here at a reduced temperature of 0.7, right? And I can reduce that by dividing by the critical point pressure, take the common logarithm of it, put it in this equation, and evaluate omega, the eccentric factor. Everyone clear about that? Yeah.
You mean, you said you find the saturation pressure and you divide it by the critical pressure to get what's in the
The
parentheses?
reduced saturation pressure,
Yeah.
yeah.
Okay.
At this reduced temperature.
Okay.
So, and we'll be able to see why this was a wise choice. It seems a bit awkward now, but we'll be able to see why that makes sense for us as we go forward a little bit. But the Peng-Robinson equation, conceived this way, if we have good values for all the properties, the critical properties and this one vapor pressure data point, is considered good enough for design purposes, that it'll get us within a couple % or so of the actual result. Yeah.
So that P superscript S subscript R is like the saturation pressure reduced, so just the saturation pressure divided by the critical pressure?
Yes,
And that's specifically
at this temperature.
okay, not.
So we find the critical point temperature, we multiply by 0.7, so that's our temperature.
Okay,
Then we look at, determine the vapor pressure at that temperature, then we divide that by the critical point pressure, and we take the log of it. Yeah. So a number of little steps there, but in the end, it's just a way of expressing that one data point. But as I was saying, the Peng-Robinson equation and the equivalent one that you'll find in a lot of books are the Wong-Suave equation, which is a similar structure of this, and it also implements the eccentric factor for its so-called third parameter. But it does generally a good enough job to actually describe volumetric behavior to within a tolerable level. Usually a few percent, generally will not make any error greater than 10% or so. And it is a native to Aspen, so it can be implemented. It's used. It's a little awkward if you're just doing it by hand. What did I have there? Oh yeah, I wanted to point out here, I'm glad I put that in, that these are all, the structure of all of these equations are cubic in volume if we work it out. So it's we know the temperature, but for that temperature we want to calculate a volume for some given pressure, then we're faced with solving a cubic equation. But it isn't let's just take a look here. While in principle you could calculate the eccentric factor just from knowledge of Antoine's equation, the textbook gives you values here, so they've done all the work for you for all the substances that they have in their database in the appendix. So there it is. For historical reasons, let me just mention a couple of other ones. There's a Beatty-Bridgman equation proposed way back in the 20s with 5 parameters. And so you should be able to fit just about anything with that, and of course that is the case. But that's very, very tedious, and you'll notice this is before we even had calculators. We're able to fit data for this for the light hydrocarbons. But that was considered not even good enough, so we would get to the ultimate here, the Benedict-Webb-Rubin equation, with 8 parameters. So here we can fit absolutely everything. Now what we require is, we've got to be careful, we can't just willy-nilly write any algebraic equation. But one of the requirements that has to be satisfied, and I'll mention others as we go, is that we recover the ideal gas law as the pressure goes towards 0. So that must be true. With pressure going to 0 is equivalent to the volume going towards infinity. So we'll notice volume in the denominator in all of these other terms. So ultimately, we will recover the ideal gas law for all of these, including these previous ones that I looked at. So that's the case. We have to insist on that, but that is satisfied in all of these situations. The structure is such that these are all equations explicit in the pressure, but implicit in V. So if you know V and T and you want to calculate P, it's a piece of cake. But if you have P and T, which is more common, and want to know V, then it's a little bit more involved. You end up having to solve roots of the cubic equation or worse. And if we want to express the equation, this is all written in terms of the molar volumes, lowercase v, but of course if we want to write it as an equation for an extensive volume, then we just systematically substitute for little v, capital V over n. Yeah.
A quick mathematical question. Because there are powers greater than 1 on all the other terms, is that why they, as v goes to infinity, those terms go to 0 quicker than the ideal gas law term?
That is a fact. I've never seen anyone implement that in a sequential way to do anything with it. The important thing is that they all go away, giving you the ideal gas law.
RT over B.
Yeah. So that's while there are probably hundreds of other algebraic equations of state that are out there and have been proposed, this is enough for you to see. So we're going to conclude that list at this point. Here's something really interesting and not that trivial to be able to understand, and we won't be able to complete the proofs at this point, but I can point out what the facts are. It turns out we can actually get the vapor pressure from a family for any particular temperature by looking at its isotherm as plotted by the equation of state. Let's look at the isotherm at 280 degrees for carbon dioxide. Here it is. And if we choose the right pressure, the vapor pressure, then I end up with a line joining the liquid behavior here over to the vapor phase behavior. And I can locate the particular value of pressure as the vapor pressure as the one in which these areas above and below this straight line are equal. So if we adjust this, we're looking for what the vapor pressure would be as predicted by, in this case, the van der Waals equation for carbon dioxide. We would move this pressure up and down until we find the pressure at which this equality between areas above and below that curve are equal. So you understand me? Now I'm giving you that as an assertion, but we will be able to prove that later. So what the suggestion here is that we've got a vapor pressure at 280 degrees here of about 51 or so. This is the tie line, you're familiar with that, joining my saturated liquid volume here to the saturated vapor volume. And the indicated vapor pressure here is about 51 atmospheres. Now to give you an idea of how rough this is, one of the most difficult things that an algebraic equation of state has to do is to predict this vapor pressure. So the actual vapor pressure at 280 is about 41. So we're quite far off. It's not ridiculous, but we are quite far off. Now the fact that that is going to be true for other substances as well motivates us to want to make use of vapor pressure data for that third parameter. So this is a motivation for defining something like the eccentric factor that includes vapor pressure data, so that we kind of force this in. Then the Peng-Robinson equation is going to get you much, much closer. Well, not surprisingly, because it's actually used vapor pressure data to actually formulate the equation itself.
Where's the critical point on that graph? Is it around 75?
Here's the critical point, isotherm 304.2, and so you can pick it out as best you can here. Oh, that's the volume, and then the pressure, yeah.
Right up there?
You
Okay.
can read it as best you can.
Okay.
So let's say we did that construction where we've equalized the areas above and below for each of the isotherms that I've got here below the critical point. And if I then joined those curves, that would give me my two-phase envelope that we've seen before. And the way we've described it before, and we see this This is the way I drew it before schematically. It's just the straight lines across joining the saturated vapor and liquid states. But if I join all those termini of the tie lines, I'm going to get the phase envelope, which we call technically the binodal curve. So it's the binodal envelope, and it encloses the two-phase region. And the way we can locate it is the way that I suggested, so we can get all of those points. But what about inside the curve further? Can we make any use out of this information that we have inside the binodal curve? Well, one thing that can be shown is, I'm not going to show it in this course, we can do stability analysis that shows us that we have one single phase stability only if this derivative partial p with respect to v at constant t is less than 0, which makes sense. It means if you squeeze on something, it gets smaller, right? If you squeeze on it, it gets bigger, then it's unstable. So this is the stability result that we have. So the curves must, if it's going to be stable, must satisfy this criterion. And what we notice is that this part of each of the isotherms is unstable. I've drawn it here at the 280 isotherm, taking us from the maximum to the minimum. So we would never expect to see a single phase in this region. So that's kind of interesting. It goes from the maximum here in the vapor phase to a minimum over here. And if I join all of those points, I get another curve inside the binodal curve, which delimits the stability region, and we call that the spinodal curve. So this is interesting. Now I've divided the region, the two-phase region here, into two parts, and it's important that you understand this. So what I have underneath the spinodal curve is totally unstable, and I would never expect to observe that. So, but what if I'm in one of these regions here between the spinodal and binodal curves? On this side, I'm going to have metastable vapor, and on the other side, I'll have metastable liquid. Let's see what I've got here next. So that's unstable. This is metastable. So also metastable, didn't have room to put in the word, but over here between the blue and the red curve. And that's metastable liquid. So what do we mean by this metastable? So let's imagine that I've got a vapor, and I'm going to be gradually increasing there's my tie line for a 280 degree isotherm. But let's imagine that I'm compressing vapor, and I find myself in this region, this metastable region. So I can actually observe vapor in this region, so this actually might be a vapor phase, but if I bump it too hard, it's going to suddenly decompose, and when it does that, it will drop down to this tie line and then split up in accord with the lever rule. Same thing if I have an unstable liquid over in this region, I'm sorry, a metastable region over here. Let me clean that off. And I'm over, let's see, I've got a point here. That will be a metastable liquid. But if I'm careful and I don't bump it, then it's going to stay a liquid. But if I do, it'll decompose and go up here and then split up in accord with the lever rule. But I never expect to observe anything between here and here in the spinodal region. If I do suddenly get myself, if I make a sudden temperature change or pressure change that puts my system into the spinodal region, it will instantaneously decompose, and we even refer to it as a spinodal decomposition. Everyone get the picture here?
So the whole idea that we've been learning about how on a tie line things split to different compositions at either end of the tie line it's based on the fact that in between it's not stable. So like that's why you have the partly liquid on one side tie line.
That's all you've seen, I think, to this point. I
Yeah,
don't
we
think
never
you've learned this before.
No.
But what you have before is we get into this region, it's going to be a mixture of saturated vapor and liquid. But what I'm telling you now is it's a little bit more complicated. If you're careful, you may actually instead find yourself in a metastable vapor or metastable liquid region. Metastable means it's not the ultimate stability. Means that if you bump it by a finite disturbance, finite amplitude disturbance, you will bump it to move into the lower Gibbs free energy range, which will be on this tie line, and that's a mixture of that saturated vapor and liquid in the correct proportions. Yeah.
What would be an example of that? Like, what would be an example of like a
It's
nice-
right here. Let's say it's carbon dioxide.
Okay.
And what I'm gonna do is, let's say I'm gonna gradually decrease I've got vapor here, saturated vapor, but now what I'm gonna do is start to raise the pressure. And it doesn't necessarily instantaneously break up into a liquid and vapor mixture. I'm gradually increasing the pressure, so I'm moving up along this line and I get here. I can keep doing that until I get up to the maximum. And if I try to go any further, then it breaks up.
So the key to that is the speed at which you increase the pressure.
Say again?
The key to that is how slowly you increase the pressure. You increase
Well,
it.
yeah, you just gotta be careful. The key to it is not subjecting it to what we call a finite amplitude disturbance. That could be bumping it, it could be disturbing it in some other way.
Is it possible to go from a substance that's spinodally decomposed to one that's metastable?
No,
Okay.
that's an irreversible process and you're done when that's over. Yeah,
Is that similar then to when you bring liquid water to below freezing?
it's exactly the same phenomenon.
Okay.
So when you bring water below its freezing point, if you're very, very careful, you can get water down. It's incredible. You can get down to nearly 20 below zero on it. But if you tap the side of the beaker, bang, you've got one ice cube. So this is what we get from underneath this spinodal curve. So we get a lot of information out of these curves. And it's, like I say, qualitatively reasonable, but probably not close enough that we can use it all for design purposes. But if I built this set of curves out of the Peng-Robinson equation, we'd probably be good enough to say we're going to get it on within a couple of 3% or so. So let's say, let me talk about this a little bit before we get on. Let's say now what we want is just to solve a simple problem. I've got a given temperature and pressure, and I want to know the volume of whatever it is I've got. Now, if I've got a cubic equation that I need to solve for that, I'm out of the ideal gas range now. So the others are cubic equations. So that means I'm going to have to solve for the root of a cubic equation. Now, mathematically, you remember if I'm getting the root of a cubic equation, I actually get 3 roots, right? And that's always going to be the case. And let's say that to begin with, I'm above the critical point here, so it's just a gas. And if I'm there, to say with that temperature, 310 K is what that is indicating. And I solve for the root of the van der Waals equation, I'm going to get just one real root, and the other 2 roots are a complex conjugate pair. Right, so I get just one real root, so that's a piece of cake. But now what if I'm at a temperature which will actually explore this phase envelope? Then the question is, what if I solve that for a volume, what I'm going to get? Because this is a situation that will yield 3 real roots. And so the question we have to ask is, what do they mean? Well, there's going to be a root in the middle. You can see here, let's look at the red line first, because that's the easiest one. There I've drawn, I've assumed that the pressure is in fact the indicated vapor pressure. So I'm going to get 3 little roots. One is the saturated liquid. That'll be the lowest value of V that I get out of it. The central one here has no physical significance at all. That's occurring under the spinodal dome. The one over here will be the saturated vapor. But what if I'm not at the vapor pressure? At some other pressure, which is normally going to be the case. Then I have to ask what I get. So here I have to make a distinction on whether the pressure for the temperature of interest is above or below the vapor pressure. If I'm above the vapor pressure here, so that I've indicated what I just talked about here, how you interpret the roots that you get when you plug in your root finder. So if the pressure now of interest here is above the vapor pressure, then what I get for the low one is subcooled liquid. That's going to give me actually a stable liquid. But what I get over here for the vapor is a metastable vapor. You can see that diagrammatically here.
You still get 3 roots, right?
What?
You still get 3 roots, right?
You get 3 real roots when you're below the critical point
one of
temperature.
them, one of them is one of them is repeated, right? That's how you'd get two.
No, I ignore the one in the middle, has no physical significance. That's a root that occurs under the spinodal dome.
Yeah, but that's for when the vapor pressure, when the pressure is equal to the vapor pressure.
It's true always. The central root is never of any physical significance.
Yeah, I'm talking about when the pressure is greater than the vapor pressure.
It's still of no significance.
Well,
There's
yeah.
a central root here. Here I am greater, so here I get a root here. I didn't even put a little circle.
Oh, you do get okay. There wasn't a circle. That's what I was.
Yeah.
That's what I was asking. I thought one of them might be repeated, so I was just
No.
yeah. Okay, got it.
And then if I'm below the vapor pressure for the temperature of interest, then the low one is going to give me metastable liquid volume, but the high one gives me a superheated or stable phase vapor. So it's kind of important that you understand that when you're asked to determine the volume of something when it falls in this sort of a range. And these are all solutions. Here's the analytical equation with the right numbers put in as described by Van der Waals equation. So any question about this before I move on? So if you're asked a question like that, you should be able to just handle it. Then I'm going to move on to another really important way that we can express the behavior, at least of gases, analytically, and that is that of the virial expansion. And this is for gases only. Let me just ask, have you seen this before at all? Okay, that's sort of a subject for this quarter, not last quarter, but you may have seen it. So the virial expansion is derived on the basis of statistical thermodynamics. A long time ago, Camerlingonis, in 1901, was able to show that I could express this PV over RT ratio as a power series in the molar density. And this was rigorous. It involves here coefficients of the molar density here, B and C, as I've indicated, these leading terms, which have important physical significance. And so let's focus on that for just a moment. B, which is what we call a second virial coefficient. That raises the question of, well, then what is the first one? So perhaps 1. But anyway, we call B the second virial coefficient. And the first thing to note about it is a function of temperature only. And it represents physically all of the two-body interactions. And that's going to be overwhelmingly the majority of interactions. That is, molecules will interact with each other a pair at a time. The third virial coefficient, C here, also a function of temperature only, but that pertains to a description of three-body interactions. So if I have three molecules simultaneously interacting with one another, that's a three-body interaction. And even at very, very high density, we end up with the overwhelming greater importance of two-body interactions. So seldom does the third virial coefficient account for more than, say, 10% of the behavior. And it makes no sense at all to carry it on, but there's nothing that says in principle you couldn't go on to the fourth and fifth and sixth. You can have as many of your virial coefficients as you want, representing four-body, five-body, and so on interactions and